So Vivek is again IIT Delhi graduate. He worked with Innoplexus, then he was with Policy Bazaar. There we had a good amount of interaction with Vivek. So at Policy Bazaar, he was helping the entire Policy Bazaar create the entire NLP
Tech
solutions
stack you can
to, huh?
tech stack you can say.
Yeah, the entire tech stack for Policy Bazaar chatbot engine and the entire call center automation. So now Vivek is working with Veena AI. So I think he's the best person to really talk about NLP. So today he's going to focus on so we have been, as I said, we have been discussing a lot in previous talks about how to kind of interpret AI models, especially with regards to computer vision. Right? So he's just going to take the same lens of how to really interpret the model weights and how to do that kind of analysis for NLP models. So Vivek, yeah, happy to take the floor, share your deck and start away.
Yeah, just give me a moment. Actually, I'm just trying to share my screen.
Yeah, go
So
ahead. You should have
issues
the
with
access.
Mac.
You should have the
Yeah,
access.
so issues with Mac actually. So I think
Okay.
yeah, maybe just a moment. Yeah. Is it visible now?
Yep. Yeah. We are able to see your
Okay,
stack.
let me just let me just open presentation.
So first
Can
tell me
I
how
come
many
on?
tabs do you have open? Can you please keep
This is on lower side actually. I usually have about 50 different tabs open.
Oh, I
So,
beat
but
you by a large margin, don't you worry.
That's fair, Vivek, and
okay,
then you can
so
actually compete on that. So I'm now going on mute. Yeah. Go on, Vivek.
yeah, so okay, okay, I have prepared a short presentation, not very long, not going into too much detail, because obviously the topic is quite difficult to understand purely in terms of me just talking on the screen and telling you about. So what I've done is I've compiled a list of resources as well, which I'll share with you later on. You can go there and read about more about this stuff. And what I will do here is actually I'll encourage you more to think in terms of looking at your model and the predictions and try to understand why it's doing so. So as a data scientist, we actually don't. I have a meme here. Actually, I'll show you in a moment. What we tend to do is we tend to just jump into model building part. We don't look at the data or even look at the predictions. एक बार 96% accuracy आ गई and then we're happy and just we want to deploy the model as soon as possible, right? So that's the tendency we have been following, and it's not wrong in academic setting, but it's very difficult to do and when you are actually trying to deploy a model which will have an impact on real users. Okay, I'll give you some examples as well. So the agenda is actually first, why do we obviously need interpretation? Then how do we actually get it? And then there's been toolkit which I've been working on to explain transformers model, which is very famous for BERT models. So how we can explain the predictions of different NLP models which have built on that library. And then obviously I'll have some questions and then references which I have gathered. Okay, so this is the meme which I was talking about. So what we do is we pour the data into our TensorFlow or some other model and then just run fit or predict and then we get the answers, right? We never bother to actually, I never used to bother to look at inside our model, try to understand what it's doing. So, and that turns out to be a big problem sometimes actually when you actually take it to production and somebody asks, okay, this it has classified wrongly, can you explain me why? And you're blank, you don't have any answer, and that's the problem, right? So in the terms of this, you really need this when you are actually in a domain where it has significant impact. Like let's say you're like Kunal talked about, let's say you're in a healthcare domain, or soon there will be compliance issues as well. Let's say in obviously automated driving, if any car crash happens, then you'll, as a manufacturer, probably you'll be asked to share a report on why actually the crash happened. Okay, and there, if you know about GDPR, there's an Article 22. It's very vague, but it's a right to explanation. So in the sense, let's say you applied for a credit card or a loan actually, and they have an automated system to predict or reject your loan application based on certain features. You have a right to ask for them for explanation why your loan was rejected. It's very vague. So, but again, in future, probably it will be more clarified, and there will be probably more compliance issues wherever there is an algorithm making some kind of decisions. Right? So going forward, actually, as we move into machine learning and AI domain, this will become more and more important to understand our model and how they are making predictions so that we are able to explain it. Not just accuracy or F1 score. They will be important in academic setting or even at the earlier stages of model development. But as you take it to production, these things will become more important as well. Okay, so I'll share two instances of things where it went wrong. First was actually Amazon tried to build a system to actually filter out resumes. Okay, based on certain number of features, they inadvertently built a model which was sexist and didn't use to promote women, and so there was a huge problem with that. They eventually scrapped the project. Uh, if somebody had actually tried to figure out what features were important or what are the features the model was looking at, they probably would have figured out, okay, it probably looks at the features like male and female, those criteria were more important, and then probably they could have done something about it, right? So, but they figured it out later and they had to shut down this project. Then second, if you follow up with Kaggle, so Jigsaw is a company which is owned by Google. They actually they actually try to build, they actually have built a model which classifies comments in an online forum as toxic. So they actually had three competitions now on Kaggle. First was actually to build a model to classify toxic comments. Now somebody built the model, obviously the winners got them, and then when they actually took it to production, there were few issues associated with it. Like there was significant amount of bias in the models. So if I share some examples like this, so like some words were associated with some different class, like epilepsy was associated with toxic. Probably somebody used those in that particular context and they got associated, but this was a problem actually for the model. Okay, and so then they had to launch, they actually launched a second competition to actually focus on unintended biases in the first model, actually to remove those biases. Now they only got to know after they took it to production. That's why it's so important actually. So if the first is obviously if you have a very controlled setting where you know where your data is coming from, then probably you would not have such problem. But let's say you're operating in the wild where anybody can use your model, then obviously you're going to have some problems because you have not ever seen that data. Like Kunal was talking about epistemic uncertainty. What will happen is you can never figure out the whole domain of data, right? There will always be certain amount of data which your model has never seen and out of domain data, and that will create problems for you. So you'll always have to look at your predictions and explore. You read about these things, they have blogs and they're pretty interesting. I'll share the links as well. Okay. There's this book by Christopher, I don't remember the full name, but it's an open source book about interpretable machine learning. It's pretty good if you want to read. It's a short book. It should not take you more than one day. But it's a very good book about, it explains why you actually need interpretable machine learning and share some instances where it's been used. So if you look at why you need to interpret, first, obviously, predictions only tell us, solves us the part of problem. It tells you what it is, doesn't tell you why. That will be required because of the reasons I mentioned. And second is, let's say you're building a model, it's very easy. It will be very so easily accepted by society if you have a system where it explains your predictions. Like let's say uh, in radiology, there's a model actually, which has been used to detect pneumonia or any other thing, but it doesn't tell why it is predicting some class. Then it's very hard to understand. And if it explains, okay, because of these certain number of patches, I am telling this is this, then it's become very easy to accept as well, because somebody could just look at it and say, okay, this is good and this is correct. And obviously bias, as I mentioned. And then most importantly, as a data scientist, I feel debugging is very easy. I share a few instances. Like I trained a LSTM model to classify movie reviews based on sentiment. I found there were some words like articles a and the, or garbage words were actually very much important in my model classifier. No reason why they should be important, but they were. So those problems you can detect very early on. Okay, now different types of interpretability. There are multiple types. First is obviously global and local. What do I mean by global? Let's say you have a model, very big model. Okay, so you want to just figure out globally how it classifies into different categories. Not for a particular instance, just what are the differences. Let's say you want to break down into what are the certain different sets of rules it uses. Let's say if I talk about MNIST, then probably for class 8 data point, the class 8 data, I'll say it looks for two poles in the images, and then based on that it classifies, or two circles in the images, based on that it classifies it as a model. It is a class of 8, right? So those are the type of things which you want to do with global interpretability. It's not very easy to do in case of neural networks, because they are a very complex models. You cannot always figure out, break it down into very simple rules. You can probably try with random forest or decisions trees. You can probably build out simple decisions trees which you can use to explain your model. So we are not going to talk about global interpretability. You can obviously read about that. We are going to talk about local interpretability. What do I mean by local interpretability? Given a model and given an example, we would try to figure out, for this example, why the model predicted this class. What are the different set of features it looked at for this model? And then based on that, you can probably figure out whether it's correct or you have to do some tweaking in the model. Then there's model specific or model agnostic. So what do I mean by that is, let's say there are some methods which cannot be used for all different kind of models. Like gradient based methods can only be used for neural networks for which you have the neural network. Let's say somebody else built the model and deployed an API, you don't have access to the model. You cannot use any gradient based method for interpretability. You can only use black box testing, where you will tweak your input and then check what are the different predictions you're getting, and then based on that you can probably get some inference. So there are tools for both types of interpretability, and I'll tell you those as well. Okay, so if you have been following computer vision, you must have seen these types of images. So they are called saliency map. They actually highlight, there can be obviously different types of images as well. They highlight the pixels which are important for that particular class. Okay, so for this, like this image, the model is saying these are the set of pixels which are important for desktop computer class. And these are the pixels which are important for the screen class, which turns out to be right. Similarly, there's this for cat, and I don't know what tabby class is, but these are the things which you must see. So this is what we are aiming for. This is for computer vision. For NLP, what we'll be aiming for is maybe we get to the importance of the words, individual words which are there. Okay, how much they are important for that particular class and that particular example. Okay, now the big question, actually, how do we go on to explain these? Okay, now I'll talk about the ways in which people have dealt with in computer vision domain, and that same can be applicable to NLP with some modifications, obviously. So first, let's talk about a very simple model like logistic regression. This is simple regression, actually. So this is a simple regression equation. These are the coefficient of the x1, x2, and xn are the features. These are the coefficients of those features. If you have ever built a regression model, you would understand that if your features are normalized, by normalized I mean they range only between 0 to 1 or between some fixed constant, then you can compare these coefficients to find out which are the more important features. Let's say if beta 2 is the highest among all these, you say x2 is the most important for this model globally, not locally. Okay, and based on that, you can say, you can define feature importance as well. Okay, right? I'm not talking about the p-values which are detected to detect whether they are significant or not. That's a very different thing altogether. I'm just talking about how important they are. Okay. Now this is about generation. What about some complex models? So what basically some of the complex neural networks are like this. You give the input, there is some highly nonlinear computation going on, which I'm representing by fx, and then you get some output, right? If I can bring this down to something like this equation, then it will be very helpful for me. So what I can do is I can locally try to interpret it. So I'm sure you must have read about Taylor equation in your 12th, 10th, I'm not sure. But what it does is you can approximate any function, okay, linearly within neighborhood of some point. Sorry about this. Uh, by using this, simply linearly you are trying to approximate this. You are using the first gradient of that function, okay, in the neighborhood, right? So what we can do is let's say I've given that one example to my neural net model. What I can do is I'll just substitute this neural network model with a linear function, okay, and then I'll compute the coefficients of this, okay, using obviously I can compute the coefficients using, if you just see this, if I differentiate this with respect to x2 or any other feature, I'll just get the coefficient. Similarly, I can do here as well. That's what we say when we say we are explaining by gradients. We in neural network, we compute the gradients with respect to input, and for each input we get a coefficient, and that's basically we interpret as importance of that input. So for, let's say, if you're talking about image, the pixel is one pixel is one input, and the gradient for that pixel output with respect to that pixel is your importance of that pixel. Okay, so that is there. Obviously there are very elaborate methods to improve these type of things. We're not going through that detail, but you can always read about that. um, so I hope this is clear. This is a very crucial part which I'm trying to explain. If you have any questions, just let me know right now, because it will be very difficult to understand further parts.
Yeah, hi Vivek, can you please
Yeah.
tell me the name of that function that you were saying? I didn't get that. Name.
So
Name.
this one, so there is no name of this function. This is just neural net I'm representing by fx.
No,
Okay,
no.
so
I
any
got
neural
that.
network.
I got that. The fx is approximately equal to fa plus f dash. So you were saying
So
that.
this is Taylor expansion. This is a
Taylor.
Taylor
Okay.
Taylor approximation actually. That's pretty standard thing in
Yeah,
algebra
yeah,
actually.
yeah, yeah,
Okay.
yeah. I got it.
Okay. Any other question? Okay, cool. So then there are some tools actually to evaluate. So do these things only. So there is one which is very popular, which is Line. This is popular because of many number of reasons. First, obviously the implementation. You can find implementation in R, Python, and any other probably other language which you use for machine learning. This is again model agnostic. This does not care about the type of model you have. All it cares about is that you are getting a probability in return given the input. Okay, it works for structured data, text data, images, everything actually. Okay. So then obviously I talked about vanilla gradients like in the previous slide. So you just compute gradients of output with respect to input. That becomes your importance. Okay. Then there are a few which I'm not going to talk about, which are also very popular, which is SHAP, which is based on shapely values. It's not as popular. So Lime is in a way subset of SHAP. It's not that popular because it's very hard to compute in case where your input size is very large. Okay, it requires significant amount of computation. That's why I'm also not covering it. But for simpler problems, it can be done and it gives very good results. Then there's integrated gradients, which is an improvement over vanilla gradients. It's also, but nowadays people don't usually use vanilla gradients. People normally use integrated gradients. But also again, This is a complex topic. I have one slide which I will explain, but beyond that, I will share resources on you to understand this. So, okay. Then obviously adversarial attacks. People try to understand models. This is model agnostic method. People try to, if I talk about text, what people try to do is they change a certain number of, let's say, this example, I really liked this movie. Then they will try to change some words like liked to hate and see how his model is doing. And based on that, you can draw inference, okay, whether it is focusing on this word or not. So those are the types of attacks you could do on a model. Okay, so any questions on this particular sheet? Okay. So I'll try to explain Lime what it does. So Lime is again a way of interpreting your model locally only. Okay. So what it tries to do is I'll like try to explain this image. So let's say the plus is okay. So the plus point is my example, which I'm trying to explain, and this is a model, and this is their its decision boundary actually. So this color is, let's say, light red color is of one class, blue is for another class. I have gotten one example. I'm trying to explain the why my model actually predicted for this class. So what Lime does is, in the neighborhood of this point, it generates some certain number of features, okay, and then it trains a linear classifier on those data points. So these data points plus plus dot dot, which you see, this Lime has automatically generated these data points, and then it has trained this classifier, which is dotted classifier. Okay, now once you have gotten this classifier, then it's again simply regression, logistic regression problem. You have got linear classifier, you have the coefficients of all the features, in this case x1 x2, and you've gotten your importance. But the good point to note here is the importance is only valid in the context of this feature. Let's say your this example, if your example was probably here, the decision boundary it would have learned was this, so it's very different for that. Okay. So it's very good method actually to quickly explore uh, interpret basically your model for any model. And the good thing about this is it works for any type of model, be it text, image, or anything. They have support for everything almost, and it's well studied also. So it works pretty well. Okay, and so this is another example. Like this is particular one class, and the shaded is other class. And let's say I want to explain the prediction for this yellow dot. What Lime has done is it has generated a number of samples here also. Now what Lime does is it actually generates a lot of examples in which are very close to point, to give more importance to the neighborhood. Okay, and very less examples farther away from the point, and then it actually learns a linear classifier, which is like this white line, and then you can just figure out the coefficients, and that becomes your explanation. Okay, so any questions on this?
Yeah, there is a question on chat. Is in Lime, how is the neighborhood chosen? By Ishan.
Okay. Okay. Hi, Shantu. Neighborhood, so there are basically, it's a simple function, kernel function, actually based on an exponential. There's an exponential function, I don't exactly remember, but it gives more weight to close distance. So that's why actually there are more points selected in which are very near to this point than when you move further. So that's how it does sampling. Okay, and the similarity which you can define. So here you may consider Euclidean distance as your metric. So that based on that, actually it samples the points. Does that answer your question, or do you have any other question?
It does. Thanks.
Okay, cool. So moving on. So now gradient-based explanation, that this is most popular in context of neural networks. So as I mentioned previously, it seems very simple, right? You just compute gradient of model output with respect to input. That's what neural network do, right? So the whole thing is based on computing gradients, right? So it's very simple. So for images, it is, but again, when you try to explain that saliency map, it becomes a bit complex. But yeah, in short, that is what it's doing. For uh, NLP, it's a bit of problem because the inputs are very discrete uh, inputs, right? These are words, not pixel values, which are continuous. So you cannot directly compute gradients. So that's why people use word embeddings as well. So what we try to do is we do not compute gradients with respect to the tokens, words. We compute gradients with respect to embeddings actually. We just, once we move to embeddings, it's as simple as the image, right? It's just 2D image, the embeddings. Then you can use the same methods which are used for images. Now what you have to do, just do is, then when you have the gradients for embeddings, you just collapse them for the individual tokens. Most of the time you can take average as well, or you can use any use L norm. L norm is basically just magnitude of that uh, vector, and then that becomes your explanation for that example. I'll explain this as well. So what happens is like this. So this is a typical natural language processing model, right? So you have words, different W1, W2, this, and then you have the whole encoder and the other layers. Okay, so we don't care about this part. We care about the embeddings part only. So once you have the embeddings, now for explanation purposes, your model becomes only this. Okay, you forget about your word tokens and everything. You feed forward your model, you get the outputs, you compute gradient of outputs with respect to the embeddings which you have got. Once you have gotten the embeddings, the gradient of embeddings, what you'll do is you'll collapse them back to their individual tokens. You can compute average of those vector, or you can compute the magnitude. Okay. So any questions on this? Okay, I think probably I'm going too fast, but just let me know if you don't even understand the whole idea is. It's not, I know it's a bit complex, but the idea is you should be just getting the general intuition behind this. Okay, so if there are no questions, I'll move forward. There's one slide I've just put there in integrated gradients last minute actually. So I think there's a question. Okay, so it's just a comment. I will take it up later. So what integrated gradients does is, so there is a general intuition behind this is, let's say you have trained your model actually. So what happens is, let's say the gradients are fairly low uh, at that particular point for those important features. What I mean by that is, uh, so let's say you have trained your model. This is the pixel value for that image. So for when the pixel is value is fully saturated, when this is active, the gradients are not very important actually. Okay, so that is what it's very hard to explain, but your model doesn't generate gradients because it gets saturated. So if you ever have the function softmax function, it doesn't matter if you change the pixel values from let's say this is 80% to 100%, the model prediction will not change. That's what gradient means. Okay, it knows if 80% pixel value is a feature or 60% is the feature, then it doesn't matter if you go beyond that. So the output doesn't change, right? So it has enough information to predict. So the gradient doesn't change, and you get no importance for this. So that's what one of the problem is, using very simple gradients. So that's why these integrated gradients were developed. So what you do is simply is you not only take gradient at this one point. What you do is you start with baseline, basically. Or what we call baseline is basically an example with no information at all. Okay, so in image case, it will be just blank image with no pixel value, a black image. Okay, now what you will do is you will slowly incorporate the information of your image. So basically merge those two very slowly. You'll give more importance to your image gradually, and then finally you'll have the image itself. Okay, and then you will calculate gradients for those images along the way, and then integrate, basically sum over those gradient. That becomes your integrated gradient. It takes care of this problem where gradients become saturated for the features. Okay, uh, you when you read about this, you'll you'll basically appreciate this more, why this is important. uh, in case of NLP, what we do is we just use padding values as an example. So let's say your input was the movie was not so great. Okay, so there are like 6 tokens. So our baseline input will be pad 6 times. Okay, that becomes an input with no example. Now we'll get the embeddings of those two, and again it becomes same like computer vision model. We overlap those and then compute integrated gradients. Any questions on this? I'm sure this is probably a very complex thing and you have confusions, but I will encourage you to go and read more about this, and you'll surely appreciate the idea behind this. And this is very fascinating as well. To think about this, like someone thought it for the first time and they had this idea. It's very fascinating. Cool. Any questions? Okay.
I'm just
Yeah.
seeing parallel between this
Yeah.
NLP and the image thing, and trying to understand from the image point of view. I hope I'm doing it correctly. I mean, it's the same thing.
Yeah. So yeah, it's the same thing actually. At the end of the day, once you actually remove the token parts and you get the embeddings, it's more or less the same thing actually.
Right.
So nobody changes the algorithm. I have not been able to find out any implementation which uses different algorithm for specific NLP purposes. But once you get the embeddings, it becomes the same thing.
I worked with the visualization before on the images, but never on the NLP side. So it's much easier for me to understand from that point of view.
Yeah, exactly. So I'll share a demo. Then I think next is demo only. So I wanted to show a quick demo, so probably it becomes more clear to people. So it's a toolkit which I am working on for probably past 1 month. Given the BERT models are so actually famous now, BERT and all the different transformers models. So I built a toolkit where you can plug in. I'm working on a toolkit where you can plug in any transformer model and get the predictions there. Basically, interpretations there very quickly. You don't have to write the whole algorithm. There are toolkits, some toolkits there which are not very easy to use if you are new to this whole idea. But yeah, there are some implementations. There was a recently paper by Alan NLP, if you follow them, uh, called NL Interpret. They have a tool as well, but it's only, I think, applicable for their implementation of BERT they have. Okay, this one, I have actually 2 models here to show. The first one is IMDb sentiment actually. This is one of those example I have pulled out of the data which they have for test data. I have 3 methods which I've implemented here. First is line. I talked about integrated gradients. I just incorporated this last night, so I'm not sure how accurately this is going to work. And then there's simple gradient. Okay, so first I'm going to show line because it takes a bit of time to compute. So as I mentioned, line samples the data around the neighborhood and it feeds to model. So this is a behind the scenes, this is BERT model, and line samples around 1,000 examples. So it takes a while to calculate. So I've run for a negative class and I will just explain what this means. So given this particular text, it has figured out these examples are contributing, these are the words which are contributing positively to negative class, and these are the ones which are contributing negatively to this negative class. And you can see this is fairly good. Actually, tedious, disappointing, vomiting, needless, roots, and without are contributing positively to negative class. That's correct, right? And excellent, plenty. I'm not sure why before is there, but these are contributing in a negative way. That's good, right? That means our model is fine and working good, right? So this was pretty fascinating for me actually to see. But the only downside is, let's say if you have a very big model, for one example, it takes a lot of time. I'll just try to run for positive class. It takes a lot of time, and I'm hoping that it doesn't hang my laptop. So hopefully it will give some of the positive words which are contributing for positive class, and that's good. Let me just check. Okay, it's still computing. So if you use Lime, and that is one of the problems which you are going to face. While using simple gradient, you have to only do a backward pass once. That's very quick. Integrated gradients is again depending on how many number of points you want to integrate over, that takes time. So again, it's computationally expensive, but not as much as Lime. So,
There is one question on the chat. Vivek, maybe you
okay,
can take that.
yeah. Okay, I'm not able to.
Okay. So should I just read it out?
Yeah, you can. Yeah, can you
So is
just?
that
I'm not able to.
Rabbit has asked that can these gradient-based explanations be applied on more complex NLP problems like NER and
Right,
extracting
right.
an answer?
Okay, so I have here three models which I'm going to demo. One is for again token classification, which is NER, and another is for language model also. So it's applicable. I have just tried for three, but it's applicable for any NLP model because you're just computing gradients over embedding. So it's very simple to do for any model. It's not restricting you any way. I hope that answers your question. If you have any other, let me know. It's still taking time. Okay, so we'll just wait for some time, and meanwhile, I'll just show you one blog if I have. Yeah. So I wanted to show you, explain the integrated gradients as well, why it's what it meant actually. So as I was mentioning, so what you do is you always have, sorry. So let's say you want to explain your predictions for this particular image, which is fireboat image. It's very famous in context of explaining your models, image models. Then you choose a baseline image which has no information. So in this context of this problem, they have taken this image which is blank, no information. Then what you do is you compute these images which have slowly you are incorporating more number of features. You are incorporating overlapping the original image, okay, and then you are computing gradients over this image, and then you are basically summing up the gradients of all these images, and that becomes your prediction. Not just calculating gradients over this image once, but along the path. So that becomes your explanation, and it performs better than your simple gradients for images. I have still to figure it out for NLP, but I'm guessing it also does pretty well there. Okay, so I have the prediction is here. For positive class, actually, we get mostly negative examples, needless, without, then other are providing negative feedback for this. Positive, we are not getting any actually. So probably I need to tweak some things, but yeah, it should give us like some other features which are providing positive for this. Like there were some words in the previous example. So yeah, that was the explanation for line. be sure to actually, if you're using Lime for a complex model, be sure to have a good machine or a good server. Let's go to simple gradient and see how that works. So this is again this, okay. So here actually you get the complete sentence with the heat map actually. So here there is nothing negative actually, because gradients, and when I'm taking magnitude, there's nothing negative there. It's just whether it's important or not. So if you look at the, for negative class, it's impressive is there, which is contributing to the negative class, obviously in a negative way, but yeah, this model focuses on impressive, disappointing, timed, humor, and missing effects. So these are the words which is focusing on. So you get a fairly good idea of what, if you do it for some examples, you get a fairly good idea why your model is predicting the way it is. Okay, doubts, discovery chance. So you'll be, so when you're debugging, you don't want key it's predicting over some meaningless words, that if that's there actually, you you should know that it's going to fail when you are actually going to deploy. Okay, here also discovery channel is contributing positively. That can be good actually. It might happen discovery is associated with good movies in general, so that's why it's learned that. But yeah, you would be like concerned in a way, like if you're deploying it for only a certain domain which is for discovery channel, then probably it's problematic. Then it's going to give output only positive or negative based on that, right? So that becomes a problem there. Now let's have a look at integrated gradients, if it gives a different answer. So it takes more time than simple gradient. Okay. Okay, so it gives a different answer. Like in previous, it was focusing more on discovery channel, as I mentioned. Now it focuses on probably correct words, treasure, television, or doubts, or something like this. So then it becomes probably more clear when you use integrated gradients. So yeah, any questions on this? कुछ तो question होगा. Anyways, so you can always, I think it's getting recorded. You can always go over these and try to understand. And if you don't understand, always you can shoot me an email or message. I'll try to resolve the query. Okay, somebody asked about other type of model. Let's say I have a token classification and I have an ER model. Okay, let's say I have is going to grow. Okay. Okay, so it got two predictions, Vivek as a person and Gugu as a this. Let's say if I try to explain Vivek, it focuses mostly on Vivek, but then there are some focus on moving as well. So this can become problematic when you say it mostly is focusing on the features of word itself. So we were facing this issue when I was in Innoplexis. We were trying to build a NER model for mostly for biomedical entities, where it was just learning those entities. There were no generalization. So in this case, this tool would have been more useful. We could have seen, okay, this is focusing on just entities itself, and then we need to do something more about this. So if I click on to explain Gurgaon, I see, okay, it's focusing on Gurgaon, but it's also focusing a bit on moving, which is good. It's trying to do that. So yeah, that is this. And let's say if I try to give one example of vast language model. Um, I'm just trying to explain a fact, to show a good bias here. Just to hospital to see. Okay. So I have one mask. So if you're familiar with transformers, mask basically implies that I want to predict I want to predict for this token actually. So if you see the predictions actually, For predictions, we get family, doctor, children, boy, man. Okay, so then rush to hospital. I'm not able to see something. Okay, oh sorry, patient. I guess not. It changed actually. I just wanted to, so when I mentioned patient, actually I was trying to highlight this. It predicts doctor for this word. It's predicting the word doctor should be here. Okay, it's focusing on patient, hospital, and rushed. Okay, now if I just change it to her, ideally I have not changed anything actually. Okay, but if you see what will happen, it changes to mother, woman, and doctor gets down by 7%. Okay, now this is what you call a bias in your model. Obviously, ideally you would not want to bias against a gender or color, but because the whole neural networks are actually based, or any machine learning model is based on bias, it learns that inherently from the model. So these type of things you can always, when you are figuring out, you can always play around and try to figure out what's causing this. And if you spend some time, actually, you'll obviously get good enough insights to improve the model. Yeah.
So Vivek, I think you can help us go through the resources that you had collated. So you can just help us see what resources might be good for.
Right. So I have these resources. Actually, I have a sheet as well, which I'm just creating also. So these are different resources of links and blogs which people have written. There are some papers as well. Papers are a bit in detail around mathematics and everything. If you're into that, you can read. But there are some good blogs actually which you can read to understand these issues in detail. So I have collated this many. I'll share this link in the slide, and I'm still doing research on this. So I'll keep on improving this and probably write more about this. So you can always come back to it and read more.
So with this one other question by Sean, we'll
Okay.
just quickly take it.
Yeah.
Should I read it out?
Which one? In line, if model is nonlinear, how, and we choose the data point where the model is nonlinear in its neighborhood, since lime is linear approximation. How? Okay. So what about emoji? I'll come back to emoji. I'm not sure what is getting there. So I was explaining this. Okay, so this is a nonlinear model only actually. So this is not a linear model. This is a non-linear model only. So let's say if I had taken a point here, probably plus, okay, and it had sampled some data around it, and let's say it was, what can I say? Okay, so like if I have taken a point here, okay, it's probably a much more realistic example. It has a very non-linear boundary, okay. Then you'd get some line like this. Actually, it will not be very good approximation of your, but it certainly will be in that context. And some information will be there. Okay, again, it's a linear approximation, so it can be like this, but there will be some information there as well. And again, you're not operating in 2 dimensions, so and I'm not sure again if there is a non-linear counterpart, simple non-linear counterpart, because again, if you're sampling, you can build complex models around that as well, which give you, let's say if you are using logistic regression, we can use probably some different types of kernels to change your features into higher dimensional features and then approximate the feature importance. Then I'm not sure if Lime supports that, but that can be a good idea. But right now, what I've explained is only valid in context of linear approximation, which Lime does. But yeah, in practical experience, it does provide some good feature importance. I've not seen, even in case of nonlinear function, it doesn't work. So
Maybe,
yeah, it's better than nothing.
Maybe at that point, I mean, it depends on the resolution we are looking at. That point itself, if we just zoom in into it, can be approximated by some linear samples.
Right, exactly. So that's a very good point actually. So as I was mentioning a point here, actually, you can say how you define your resolution, right? At this scale, actually, it feels like this is a very non-linear, but if you zoom in and look at very small scale, you can understand, okay, this probably is not linear at the end, right? So if you have smooth function and not very non-linear function, it's going to, that's the property, right? So it's going to be linear at very small scale.
This is something which is used for I don't know if you guys have seen. I mean, when people explain the loss curves and all, these are approximation, and these approximations are valid because each of those small portions are kind of just some linear steps basically. So it's like when we do integration, we do some stepwise integration to justify the value. It's just that the resolution decreases. The finer the resolution is, the better the integrated value is. Same way people explain the loss functions as well. The function that is approximated by neural networks as well. They just say ki in that close proximity, it is linear step function which can be approximated like that.
Right. So any other question? That was a very good question actually. So any other question?
Sorry, you are asking what about emoji? Can you please explain what exactly
Yeah.
you know?
Yes. So actually, what happened, like when you are doing that embedding for the emoji, you generally use some other embeddings from some other package or something. So I was like hoping, like if we are doing some concatenation between two different type of data, one is suppose text, another suppose is emoji or some other
Right.
like sticker or something. So in that
Right.
kind of scenario, how those line and those integrated gradient explanation can actually help.
Right. Right. So see, what I'm saying in that case, actually, let's say if already BERT has 3 different embeddings, right? So it's not one embedding. So they have
Yeah.
position embeddings as well, right? But the thing there is, for every token there is 3 embeddings, not one embedding. So if there are, for every token, if you have multiple embeddings, you can just concatenate them and get a final embedding, right? And
Yeah.
then compute gradients for that. But let's say if you're talking about some setup where you have different gradient, different number of gradients for different number of tokens, that's a very different thing altogether actually. Okay. But let's say there's a model which we are trying to build where we had character level embeddings as well and word
Yeah.
level embeddings as
Yeah.
well,
Exactly.
right? So in that case, eventually what you do is for character level gradients, you bring down them into word level embeddings as well, right? So you do some sort of max pooling there, and then you concatenate them both before feeding down to probably LSTM model or any other model. So you can compute gradient from that point onwards. So once you have a representation for each token, so that's not a problem itself. Okay, but eventually you will get interpretations for each individual word only. Or you can do like this, you can explain character level wise as well. So there had been some papers on that as well, if you want to do.
So like to summarize this thing, like like if we actually have a character level embedding, then that saliency map will return some character level saliency on that whole text, right? So
So
is it something
if your
like that?
model if your model supports character level, so like if you have character level embedding throughout, then you'll get obviously character level explanation. But you have like word level, and then you're doing some other processing on characters itself, then it's a very different thing actually which you're doing. So you probably will have to write your custom explanations in that sense. Or what I was talking about is if you are finally merging those embeddings into main word embeddings, right? Then you can use that again in this context only. You can use those embeddings final merge one to explain. That will be okay. So if you want to discuss in detail some specific problem, you can talk to me later. Actually, I'll
Yeah, yeah,
probably try to help you out.
yeah, sure.
Good. Yeah, thank
Thank
you,
you.
Vic. Thanks a lot for this. Pretty
Yeah,
interesting. Good to see the demo.
yeah,
Yeah.
cool.
So again, I had that Ravikant's context of doing a lot of this on images, so it was good to kind of see the same problem applied to
Yeah.
same kind of thinking applied to NLP problems. But yeah, so let's